Hi all. I'm going to continue on with the whole representation of what a molecule looks like. You know, we've talked about Lewis structures, and I want to start with that and then go into something that is a little more accurate than Lewis structures, and we'll take it from there. Okay, so let's look at my OneNote here. All right, last time we talked about Lewis structures, and I left you with, I wanted you to figure out a Lewis structure with this formula here. And I wanted you to also do some additional alternative structures. Now, the issue with Lewis structures is it takes a formula, which is kind of minimum amount of information about the chemistry of that compound, and it puts it into a structure. And then from that structure, you can then formulate the chemistry. The problem with Lewis structures are they're two-dimensional, they're flat. And in reality, structures are three-dimensional, not two-dimensional. So what we're going to do is first look at the C2o2H4 structure, which is the structure for acetic acid. And this is the Lewis structure, one of 8, by the way. And I asked you to do 3 additional structures. Okay, so if we look at this, you know, we put the carbons down first because they have the most singletons. Then we surround it with oxygens and hydrogens on the outside. And then we make bonds with everything first. And then we had some leftover singletons over here with the oxygen, so we made another bond there. So now we're all done. Let's look at whether this is legal or not. Okay, so let's first look at the number of bonds. Carbon needs 4 bonds, oxygen needs 2 bonds, hydrogen needs 1 bond. Okay, so this carbon here we have 1, 2, 3, 4. This carbon is 1, 2, 3, 4. The oxygen is 1, 2. Oxygen is 1, 2, and hydrogens are all 1 apiece. So this, from a bond standpoint, this is legal. Let's look at full shell. The full shell is going to require 8 electrons, and that's shared. So for carbon and oxygen, and 2 for hydrogen. Carbon has got 2, 4, 6, 8, 2, 4, 6, 8. Oxygen's got 2, 4, 6, 8, 2, 4, 6, 8. So, and then hydrogen's got 2 apiece. So this is a legal structure. And this is, in fact, what acetic acid looks like. However, with C2o2H4, after we put in the lines, I asked you to do 3 alternate structures. Okay, and there are at least 8 total structures. Here are 7 more that are totally legal, and of these 8 structures, the only one that really chemically fits the bill in terms of once you do chemical analyses on the structure is this first one we did. But the bottom line is all of these are legal. Excuse me. So on a test, if I asked you draw 3 structures, 3 Lewis structures with this formula, any 3 of these would be fine. Any 3 of these would be fine. Now the deal is, as I was saying earlier, these are flat, 2-dimensional. And in life is 3-dimensional. So there's another process we can put this formula through to create a 3-dimensional version of it. And that is called valence shell electron. That means the electrons on the outer shell pair repulsion. Now, as you know, electrons repel each other because they're both of negative charge. So if we were to minimize the repulsion of electrons on a molecule, that would be the most stable state of that molecule. And that's what this 3-dimensional structure is based upon, is what is the most stable positioning of these electrons that will allow the most stable structure. Sometimes it's two-dimensional though, and sometimes it's three-dimensional. The bottom line though, if it is three-dimensional, it will show it. Okay, so some definitions now. Now we abbreviate this valence shell electron pair repulsion as VSEPR or VSEPR. All right, so we need some definitions here. One definition is central atom. Central atom has two or more atoms bonded to it. If there's a central atom, you need to do a VSEPR analysis per central atom. So if there are three central atoms, three analyses, okay? So let's look at real quickly acetic acid, okay? So the hydrogens only have one atom attached, so they're not central. This oxygen here has one atom attached to that carbon, so it's not central. This oxygen, though, has two atoms attached to it, hydrogen and the carbon, so it's a central atom. So this model here has three central atoms. Hence, we're going to have to do three analyses for this particular molecule. Okay, so bottom line is, this whole thing is centered around the central atom. Okay, now the next thing we have to figure out is, for example, if we were looking at carbon dioxide, this is the Lewis structure for carbon dioxide. We start off with the carbon in the middle, oxygen on the outside, and we attach one bond to each one. In fact, let's just do that. Okay, so we'd attach one bond to the carbon and oxygen, and then we do the analysis. Are there any singletons left over? Yes, there are. There are two singletons there, two singletons there. So now we have no singletons left. Okay, so if we arrange the dots, if we arrange the electrons, it'll look a little neater doing it this way down here. Okay, so this is a legal structure. Carbon has 4 bonds, 2 double bonds. Oxygen has 1 double bond. Other oxygen has 1 double bond. So as far as the bonds go, this is legal. Each have a full shell of 8 electrons, both the carbon and the oxygens. Okay, so if we replace the dual electron bonds with lines, we'd end up with this over here. Okay, so first step, whenever we do a VSEPR analysis, we have to do the Lewis dot structure. So step number 1, Lewis dot structure. And what I've done is I put a worksheet together for you here with all the steps for VSEPR. Now, let's just put and I have copies of this on Canvas modules. So you can print these off if you want. Okay, so the first step in the VSEPR process is to do the Lewis dot structure. Okay, so if we were looking at carbon dioxide, this would be the Lewis dot structure here. Okay, step number 2 is the number of electronic domains. That's a fancy word for how many electron groups are there. Now let's look at this, okay? So here's a group, here's a group. Doesn't matter if it's a single, double, or triple bond, it's a group of electrons. So this has 2 electron domains or 2 groups of electrons. So in our worksheet over here, we are going to put, we would put 2 here. Now with 2 groups of electrons, the most stable place for electrons to be is 180 degrees apart, directly opposing one another. And we're going to call that structure linear because it's like a line. Okay. All right, what if it has 3 electron domains or groups, like BH3? This would be BH3 here. So we have 1, 2, 3 electron domains, or 3 groups of electrons. And the name of that structure is going to be trigonal planar. And that happens to be, instead of one-dimensional, it's two-dimensional or flat. So this is 1D, 2D. Okay. And the third structure, now I'm only going to go over 3 structures for our Chem 300 class. When you get to 400, there are 5 of these. Okay, but I want to focus on the first 3 so you get this down perfectly. So when you take 400, when you're going into the 5th and 6th, it'll make sense. You're just adding a little more complication to it. But I want to make sure the fundamentals are down perfectly before you get into 400. Okay, so let's look at, this is called carbon it's called carbon tetrahydride or methane. Excuse me. All right, this is the Lewis dot structure, and this is going to be the 3-dimensional version of it. Now, this would have 4 electron domains or 4 groups of electrons. 1, 2, 3, 4. However, the best way we can represent those 4 groups of electrons in 3-dimensional space is not putting them on a 2-dimensional plane, but putting them in a 3-dimensional sphere. And what it looks like is like a pyramid. So we're going to put 2 of the groups. Now, I'm not talking about the hydrogen, I'm talking about electrons now. The first segment of this is on electrons, electron domains. So we're going to put the 2 of the electron groups on a flat plane. And then another one is going to stick out here, represented by this triangle. Triangle sticks out. The dotted one goes into the page. So now we have a 3-dimensional, it's like a pyramid, a 4-sided pyramid or a tetrahedral. Okay. So when we're looking at the best way to put electrons around a central atom is we have 3 situations. We have 2 groups, 3 groups, or 4 groups. And again, when you get into Chem 400, you'll have 5 groups and 6 groups. They add quite a bit of complexity when you get into particularly the 6th group. Okay. All right, so that's kind of the first thing you're going to do. So let's look at an example. Okay, let's look at NF3. First thing you do is the Lewis dot structure. Okay, so let's do the Lewis dot structure for NF3. So it's going to look like this. Okay, how many electron domains or how many groups of electrons do we have? We have 1, 2, 3, 4. So that unbonded pair of electrons counts because it's a group of electrons. And what's the electronic geometry? tetrahedral. Okay. It's going to look like this right here. Only it's going to be B, and then we're going to have one of these come out. And one of them go into the paper. So that's the first thing you do, is to figure out the electronic geometry. Let's do another example. Let's do water. Okay. So here's oxygen. Two hydrogens. Okay. So how many groups of electrons do we have? We have 4. 1, 2, 3, 4. 4 groups of electrons. That again is tetrahedral. Okay, let's do another one. Now I'm going to be continuing on with these. I'm going to be adding some other stuff over here. But the first step is going to be determine the electronic geometry. And that basically is counting groups of electrons. Okay, so let's do HCN. So this is what this looks like. Here is our carbon. Here's our hydrogen. There is our nitrogen. Connect everything together with one bond. And then we're gonna hook up now our singleton electrons. And there are 2 groups. Okay, so how many groups of electrons are there? Well, there's 1 group, 2 groups. And what's the geometry of 2 electron groups? Linear. So one bond, single bond, double bond, or triple bond is 1 group of electrons. 1 group of electrons. Okay. So there are 2 kinds of geometry we're going to be talking about. One's electronic geometry, and the other is molecular geometry. And they can be the same or they can be different. It depends on this here, lone pairs and bonding domains. Now I've given you some homework here, which is down here. Giving you 15 problems for homework. 1 through 6 is 1 central atom. 7 through 15 can be anywhere from 2 to 4 central atoms. Each central atom needs to be analyzed, just as we're doing this here. Okay, the next thing I want to talk about is molecular geometry. And we just talked about electron group geometry or electron domain geometry. Now we're going to talk about molecular geometry. And that is determined by the number of bonding and non-bonding domains. A non-bonding domain is another way of saying electron pair. Bonding domain means with an atom. Okay, so if we go back to carbon dioxide, it's going to look like this. And it has no, we're talking about the carbon now, because the carbon is a central atom, not the oxygens, because the oxygens only have one atom attached. Carbon is the only one that has two or more atoms attached. So carbon is a central atom. Okay. All right. It has no pairs. Again, the carbon now, we have to kind of ignore that. So we're just looking at the carbon now. Carbon has two double bonds. It has no pairs of electrons that are non-bonded. Okay, so that means that is 2 and 0. So that means the molecular geometry is linear also. So in the case of two electron domains or two groups of electrons, the electronic geometry and the molecular geometry are the same, which is linear, and this is 180 degrees. Okay. We're looking at boron trifluoride, BF3. It has 3 electron domains. It has 3 atom bonding domains and no electron pairs. That's called trigonal planar. And that is like this trigonal planar. This is 2-dimensional. This is 2-dimensional. And that angle is 120. In this molecule, nitrite, we have 2 bonding atoms and 1 non-bonding electron group. And that's this right here, non-bonding, bonding, bonding. So this is the non-bonding. These will be bonding. And that's called bent. Because if you ignore the non-bonding, the molecule sort of looks like this. And this is where the bent comes in. Sometimes they call it angular also. Most of the time they call it bent, however. Okay, in the situation down here where we have 4 electron domains, then we can have 3 situations. We can have 4 bonds, no electron pairs, 3 bonds with atoms in 1 electron pair, 2 bonds and 2 pairs. Okay, so if we look at methane, we have no electron pairs, so it's going to be 4 and 0. That then is going to be tetrahedral molecular geometry. If we're looking at 3 and 1, 3 bonding, 1 non-bonding, it's going to be similar to ammonia NH3. And if we're looking at 2 and 2, 2 bonding, 2 non-bonding, like with water, it's going to be called bent or angular. So, going to our worksheet over here, let's go up to nitrogen trifluoride. So number of bonding domain is going to be 3. Lone pairs is 1. So the molecular geometry is going to be trigonal pyramidal. Now be careful with trigonal, because trigonal can be planar or pyramidal. The bonding angle is, it's less than 109.5. We're going to talk about polar later, so don't worry about that right now. Okay, let's look at the water. Okay, so how many bonding and non-bonding we have? Okay, we have 2 bonding, 2 non-bonding. Okay, the geometry that is bent. Bond angle, again, is 109.5, and it's much less than 109.5. Okay, let's look at hydrogen cyanide. This is hydrocyanic acid. It's very, very, very poisonous. This is what they use to gas prisoners when they were in the gas chamber. It's also what Nazi Germany used to gas the Jews in the concentration camp. This stuff is very, very, very deadly. What it does, it binds up your hemoglobin. So your hemoglobin cannot carry oxygen or carbon dioxide. Okay, so we analyze the Lewis dot string. We have 2 electronic domains. That means electronic is geometry is linear. It has 2 bonds. That's the CH and CN, and no non-bonding. So that means this is linear. So with 2, we have linear electronic and linear molecular geometries. They're the same. The angle is 180. So that's 3 examples. And what I'd like to do is stop here. I'd like you to practice this. What I want you to do is go through the first 6 examples. Here. For sure, get those down. Now you have the weekend to work on these. On Monday, I'm going to review this again using 7 through 15 examples where we have multi-central atom examples. Okay, and I know this is a non-question lecture, but I'd like you to practice this. Please send me an email if you'd like to do a Zoom session. This weekend, I'm going to be busy on Saturday, but we can do it on Sunday. I'd be more than happy to. I just need a heads up on it.